So the objective of this lab was to compare the bending measurements between an unknown angle test and a three-point bend test. Beam bending is when a beam deflects because a load is applied perpendicular to its length. This creates tension on one surface, compression on the opposite surface, and a neutral axis in the middle where strain is zero. In this lab, 3 points bending setup. The applied displacement generates a bending moment that increases toward the center. And we use strain gauges on the tensile side to measure the resulting surface strain and compare it to the beam theory predictions, which leads us into the methodology. For the methodology, first we attach the strain gauge to a beam and perform measurements before applying force. First, uh, for the first test setup, we included which included a small beam, and we applied force to each of the ends over an unknown angle. For the second test setup, include a three-point bend test using a vise, and um, and the force was being applied to the center, which led us into our data collection.
Here we have the table of the collected and calculated data. The collected data is taken 20 points from the video that we took of the experiment. We took the video of, we have the force that was taking it from it, the displacement that was taken from it, and the V strain, which was taken from it. The force was taken from the load cell. As we applied the load, the force increased. The displacement, there was a gauge on there that increased as we increased the load. The displacement also increased, which we'll see in the graph on the next slide. And in our case, as the displacement increased, the V strain got smaller, but in most cases it'll get bigger as the strain gauge bends a little bit, it'll increase the load. But in our setup, the wires must have been flipped, therefore it shows it as decreasing. V out next to V strained is calculated just by um, doing the offset of the V rest, which is that first value of the V strained. Bending moment calculated using the equation found in the lab manual. Same with the stress and strain, both just using the force and displacement data taken from the video and using the equations, we calculated it as shown. Um, and going to the next slide, we have the two graphs, the force and displacement graph and the stress and strain graph. As you can see, the force and displacement graph, it's has a bit of a linear section. Then you can see it bends over a little bit and then gets a little bit more linear. So the first section would represent the elastic region all the way up until probably that about 0.03 inch displacement. And then you can see where it becomes plastic a little bit and then so on. Uh, Moving on to the stress strain curve, it's a little off. We couldn't quite figure out exactly why it was off. Looking with the TAs on our equations and the data we collected, it all looked good and relevant. The only thing we found that could cause this is during bending, some air pockets develop within the strain gauge, which cause a little bit of the mix up between the voltage that we received when displacing it, which could cause the error in our stress strain graph as seen. Moving on is our displacement and length graph. This is taken by doing 50 points all the way up the line up to the midpoint of the beam length. So from 0 to L divided by 2, and then using the V of X equation given in the lab manual, you can calculate using the max load
The whole
from
thing of pumpkin bread?
the the max load from the video and data collected, and it you get a nice curve which represents the deflection of the beam. So the blue line would be the beam bending itself.
Yeah, so as Logan just said, the shape of the curve does match the deformed beam observed during our experiment. And from our results and analysis, comparing the modulus that we found to the theoretical modulus, the percent error that we found was only about 25%. So it's pretty good comparing that to the theoretical value that we had, which leads us into our discussion.
All right. So then for the discussion, saying again that the shape of the curve matches the um, like the what actually happened in lab with a 25% error. That's pretty good. Um, Also, the force versus displacement graph, um, and like both of the graphs had a pretty good R squared value, meaning that they were just a strong fit. The second one was a little bit less, but as Logan said, that was um, we couldn't really find out why that was, but and then the voltage also increased linearly with the beam deflection. So then for our conclusion, with 25% error, we could say that this lab was successful in finding the Young's modulus of the sample. And some possible sources of error for this could have been that the sample was slightly misaligned on it. The glue or tape could have been ineffective in actually like securing the strain gauge to the sample, and that would have caused a fluctuation in the output in our Excel like data. And then also although it would have had a little bit of a lesser impact, the temperature in the room, like during the lab, could have affected the strain output. So then for our future work and recommendations, we could use different materials other than the sample that we did during this lab. We could have done like, we could do some sort of metal, maybe a different type of plastic. And then for second, we could use different, like multiple strain gauges, and way we could map the strain along the beam. And here is our references.
Thank you for listening.